Hello friends, welcome back to C Feel Academy, where we learn together from each other. So today's topic is quick shot. So this is in continuation with series of videos we are creating to explain sorting algorithms in the context of computer science. So friends, let's get started. So these are the subtopics which we are going to cover today. We'll get started with what the sorting problem is, just a basic introduction to what the sorting problem means, and then we will see a little bit about overview of quicksort. Then we will move on to the basic strategy or the basic idea behind quicksort, how it actually does the sorting, what strategy it uses, and all that. Then we will move ahead and see the actual pseudo code for the algorithm, the steps that the algorithm contains. We will go through it step by step and try to understand it. And next we will go ahead and apply the algorithm to the basic to a real life, to an example of an array, and we'll try to sort that, and we'll see that example in very great detail. So the purpose is to make you understand the step by step running of the algorithm. So once we do that, we will then go ahead and do a performance or a complexity analysis of quicksort, and finally, as always, we will end with an exercise for you guys. So an important point to note here is, if you want to understand what sorting algorithm is and the various popular sorting algorithms we have, I would recommend you to look at the introduction to sorting problems algorithms video that we have. In that video, we also compare the various popular sorting algorithms, so you'll get an idea where quicksort actually fits in, and you'll also get to know how to do complexity analysis using basic algorithms, using basic techniques. So I'll make sure to link that video over here. So friends, let's get started with the introduction of quicksort. So first of all, let's see what a sorting problem is. So a sorting problem, as you might already know, is nothing but arranging the elements in a particular order. So let's say we are given a sequence of n numbers, let's say a1 to an, and we are assuming it is part of an array where these elements are contiguous, which means they are located to each other. And one way to sort these numbers may be to just sort them in ascending order. That's probably the simplest way to sort a bunch of n numbers. So we are assuming that we have n numbers here. You may also have, let's say, a bunch of words and you want to sort them as dictionary. So the strategy will be the same, but in that case the sorting will be probably lexicographic order. But here, let's just for simplicity consider we have n numbers. So when we have an input of n numbers, the output is necessarily an ordering of the numbers in such a way that the numbers are in ascending order. So which means once we are able to arrange them into numbers a1 dash, a2 dash, dot dot an dash, the input sequence will be such that a1 dash is less than a2 dash, a2 dash is less than a3 dash, and so on till an dash is less than an dash, an minus 1 dash is less than an dash. Alright, cool. So let's see what is quicksort and where it fits in. So quicksort, as its name suggested, it's a quick form of sorting, although it it may not be quick always, but it's a sorting technique which uses the divide and conquer approach. So divide and conquer approach is the second type of technique which we had discussed back earlier in my other video. So the first kind of technique was just running through the array using multiple passes, and the second technique is divide and conquer. So what happens in divide and conquer is we just divide the original problem into smaller subproblems, and then we solve the subproblems, and then finally we conquer, which means we merge those smaller subproblems to get our final output, merge the smaller solutions to get our final output. So how does quicksort work? So quicksort, what it does is when we are given an array, let's say we are given this array, first step is to just select a pivot, which means randomly select an element and make sure that element in its original position. Which means, let's say we select this guy, this element as our pivot, and we have to make sure that element in its position. So which means the other elements to the left of it might not be sorted with respect to each other, but they are sorted with respect to this element. Or in other words, all the elements to the left of the pivot are less than p, are less than the pivot, and all elements on the right side are greater than the pivot. And then once we do that, we now have two arrays, which is the left one and the right one, which can be sorted recursively. So this is how the array is divided into smaller subarrays. And then finally, the same process is repeated or recursively done. The same process is recursively used, and then the separate array is sorted. I mean, the smaller subarrays are sorted as separate arrays. So what is the property of quicksort? It's a recursive algorithm, which means it runs through a copy of itself. So which means the size of the array is reduced, and then the same algorithm is called. It is in place, which means we don't need any additional space for doing the sorting. But the algorithm is unstable. So which means if we have two elements in the array whose values are same, now the order of the elements may not be, order of those same elements may not be same in the final output array. And finally, it's not online, which means it cannot operate on streaming elements. So it needs to see the entire array before doing the sorting or before applying the algorithm. Alright, cool. So let's go ahead and now see the basic idea behind quicksort. So we have discussed slightly, but here we will discuss it in very greater detail. So the first step of the of the algorithm is, first of all, as we already discussed, just select a pivot, any pivot. And in fact, selection of pivot itself based on different strategy might lead to different results. So we will discuss that in a bit. And then the idea is to position it into correct place in the array, dividing it into two. And this process is done by repeatedly comparing and moving the greater elements to the right side of the pivot and smaller elements to the left side of pivot through exchanges. Once the two smaller arrays are created or partitioned, we just use the same process, which means we use the quicksort process recursively till we are done. We are remaining with just a single element. So let's see how it looks like visually. So let's say we are given this array. We initially select a pivot P, which is located at this location, and then we have the left side of P we have certain unsorted elements, right side of P we have certain unsorted elements. So we move those elements, and then we make sure that all the elements that are on the left side are less than P, which is here, and all the elements to the right side are greater than P. Once we have done that, now what we do is we repeatedly apply quicksort on the left side and the right side of the array. So it will look like this. So in the next step, we have two arrays. One will have 3 elements and the other will have 5 elements, and we will select a pivot again on the smaller array, and then again do some exchanges and make sure that the new pivot is in its original position. So which means the items to the left of P are less than P, items to the right of P are greater than P. Same thing happens with the other element, and we choose a pivot and make sure that the elements to its left are less than P and the elements to its right are greater than P. And then we repeatedly do that till we are just left with single elements in our smaller partition, and at that time we can say that the array is actually sorted, because we would have done exchanges, or we would have moved elements in such a way that the entire array would now be sorted. Awesome. So this is how it looks like. Next, let's go ahead and then see the actual algorithm in steps. So here is the actual algorithm that is. So it's a very small algorithm, but it actually uses a partition procedure in between, or a partition algorithm call in between. So what the algorithm does is it takes a, which is the array, it takes low and high, which is initially low is actually 0 and high is the size of the array, which is its n. And what it does is, if it checks if low is less than high, so which means if the size of the array is at least 2, if it's only 1, then there is no need to do any exchanges, we can just return. Or if the size of the array is even lesser, like there are no elements, then we don't need to do anything. But if we have at least 2 elements in the array, which means in step 2, so this is how it is. So let's say we have high and low, so low points to the lower end of the array, high points to the higher end of the array. And in step 2, what we do is we call a partition method. We'll see what this partition method is in a short while. But let's say we have a partition method which takes the entire array low and high, and it returns a position p, which is nothing but the position of the position of an element, in such a way that the left elements are less than p and the right side elements are greater than p. Once we have that, then we just need to call the same algorithm again, which means what we do is we now call quicksort on the smaller array, which is a, low, and then p minus 1. Notice p is in its sorted position, so we just need to sort from 1 to p minus 1, which is low, to p minus 1, and on the right side, which is a, p plus 1 to high. Alright, cool. And then this algorithm continues, so which means this is a recursive algorithm because it calls in itself, and then it it does the calling till low is less than high. Whenever the size of the elements or smaller sub arrays will be less than 1, or sorry, less than 2, then the algorithm will exit and then it will return. Alright, cool. So till now it was fine, but let's go ahead and see the partition method now, because that is the most important part in quicksort. And notice the partition method, the choosing or the choosing of the pivot in the partition might slightly vary in different books if we are going through the algorithm, but in this case what we do is we just choose a pivot which is the middle element of the array, just as a convenience. But some books choose the leftmost element as the pivot, some choose the rightmost element at the pivot, and depending on that, you might have different versions of quicksort. So what does partition do here? Partition takes low and high, which means the smaller end of the array and the higher end of the array. And let's first start with assigning p as a high plus low by 2, which means we will just choose the middle element as partition by just convenience. So p points to the middle element, as we see here. Next, what we do is we initialize 2 pointers, I, which starts from low minus 1, and j, which starts from j minus 1, j high plus 1. So which means we start from the leftmost end of the array and the rightmost end of the array, one element greater than that. Alright, cool. Then we go to step 3. Now what step 3 does is it says while I is less than j. So what we are just going to do is, our approach here is we are going to move I to the right and move j to the left till they crash with each other. And what are we going to do when we move I to the left? So we will see an element, repeatedly we'll compare each element with p, repeatedly we'll compare, and then we will see if there is any element that is out of place. So which means when we are doing from the left side, what we do is we go to step 4, we say I equal to I plus 1 while ai is less than p. So we increment I 1 by 1 till we reach at a point such that AI is greater than P. So which means if AI is less than P, we just continue. So if there is an element that is less than P, it's fine, we don't need to swap actually, or we did not do so, which means that element is okay with respect to P. All elements that are smaller than P should be to its left. So let's say we increment I and we find an element X that is greater than P. So we will stop here, we will stop the I pointer here. Then what we do is we go to the fifth step, which means now we will decrement the J pointer. So J will now similarly, so what we do is we do J equal to J minus 1 while AJ is greater than P. So we start from J equals to the high plus 1, and we keep decrementing till we find another element that is out of order with respect to P, which means we have found an element Y that is less than P. So because the element Y is less than P, it has to be on the left side of P. And once we have found such an element, we will stop. If we haven't found, we just keep decrementing J till till I and J will collide. So let's say at some stage we have found an X that is out of order and Y that is out of order, which means X is greater than P and Y is less than P. Then what we do is we go to step 6. In step 6 we will check if I is less than J. So which means if we haven't crashed, so I and J haven't crashed, so which means we are still on our ends and doing our basic checks to see if we have found an element out of order. Then we just swap those two elements. Now in this case what we do is we just swap X and Y. Once we swap X and Y, notice what will happen is both of them will be at proper position. So which means we will have X which was greater than P to the right side of P and Y which was less than P to the left side of P. Alright, done. And then once we are done, we repeat the process again. What do we mean by repeat the process again? We will go to step 3 and then we will check again, is I less than J, which means are there still more elements to be compared with P and to check if they are out of order. If yes, which in our case it is, so what we do is we again increment I till we have found the first element that is out of order. So let's say somewhere we keep doing this, and at some point I and J will be pointing to the same location. So at that point what will happen is the outer loop will now fail, which means while I less than J will no longer occur, so the outer while loop will now break. So we will go to step 7 and then we will return J, which means we'll return the element where J is pointing to. So that element is now in its position. So all elements to the left side of it, which means all elements over here are less than the pivot, which is less than J, and all elements to the right will now be greater than the element. So then we just return that value J, and that value now goes, I'll go one slide back, so that value is now returned here as partition P, and then as the pivot P, and then we will sort the left side and the right side of the array, and then we keep doing that. Alright, cool. So I hope this explained a little bit, or at least a bit more in detail, but let's just try it on a concrete example. So let's just try it on the example, in fact a very detailed example I would say. So let's say we are given this array which has 9 elements to be exact, 9, 2, 7, 4, 6, 11, 3, 5, 10. I think we have been using this same array or similar arrays in all our sorting algorithm videos. So we are given this array and our job is to just sort this array. So how do we start? So first step is, since quicksort is a recursive algorithm, we have to make a call, and what we do is we make a call of quicksort with low and high. So low is 1, which is the first element, and then we pass in the last element, which is the length of the array A, or in this case let's say this is 9 because length of the array is 9. So here is the algorithm we have, just for our reference, so that as we go through step by step we are able to follow it. So let's go and execute the first step. So step 1 says if low is less than high. Now in our case low is 1, let me write it down here, high is 9, so low is less than high, which is true because low is 9 and low is 1 and high is 9. So let's assign it. Low is now 1 and high is 9. High points to the 9th element. What we do is first we call the partition A low high, so which means it will call partition A19. Cool. So let's go ahead and then run the partition procedure now. So here is the partition algorithm or the procedure, and here is our original array. We have low pointing to 1 and high pointing to 9 as we already discussed, and we are running a partition A19. So the first step that partition does is it chooses the middle element as the pivot. So P is A high plus low by 2. Now high is 1, 9 is 2. So 9 plus 1 is 10 by 2. 10 by 2 is nothing but 5. So basically this is A of 10 by 2, which is A of 5. So our partition P will now point to the fifth element. Fifth element in our case is 6. So let's say we keep a value of P equal to 6. So P is now assigned 6. Next we initialize two pointers I and j in step 2. I points to 0 because low was pointing to 1, and sorry, there's a small mistake here. This should be 9 because this is high, this should be 1. Alright, so I is 0, 1 minus 1 is 0, and j is high plus 1, which is 9 plus 1, it's 10. So it points out of boundary at the moment. And then we go to step 3. Step 3 says I is less than j, which is true because I is 0 and j is 10. So what is the first step to do? We increment I till we find an element that is out of order in step 4. So which means we check if ai is less than p, then we just keep incrementing. But if we find an element ai that is greater than p, we have to stop there. So let's see what happens. So we increment I first, so I becomes 1 now, and let's now see if ai is less than p. So ai is 9, in fact 9 is greater than p. So we have already found an anomaly. We have already found an element that is less than that is greater than the pivot on the left side. So we have to stop here. So we'll stop here, and then what we do is we break out of that loop in step 4, and we will now go to step 5, which is the j loop. So what it suggests is you decrement j till we find an element aj that is less than p, or while aj is greater than p, we just keep decrementing. So first we decrement j, so j now becomes 9 from 10, and we compare 10. In fact 10 is greater than 6, so we are okay here. So we don't need to stop, we'll keep decrementing j because we have aj as greater than p. So next step, again j becomes 8 here, and the value is 5. 5 is less than 6. Cool. So we have found a point where we need to stop because aj is no longer greater than p, aj is less than p. So which means we have to stop here. So the inner while loop will again stop on step 5, and we will go to step 6 now. In step 6, what happens? We first check if I is less than j. I is definitely less than j because I is 1 and j is 8. So once we have found, so which means we have already found two elements that are out of order, and we can just exchange them or keep or order them. So we swap those elements as we have in step 6, swap ai aj. So we'll swap these elements, and what will happen is finally once we swap, so this is the values that we have, 5 and 9 are swapped, we are done with step 6. So which means we'll again return back to step 3 to see if I is less than j. I and j, I is still less than j, which means there are still more elements to be covered to be seen if they are properly positioned according to the pivot. So first step, which means in step 4 we will first find an element and keep incrementing I to find an element that is out of order. So I is 1 now, I becomes 2 now, and we compare 2 with 6. 2 is less than 6, so we are good here, which means this element is okay. So we have to increment I further. So I becomes 3 now, and we have found 7. And notice 7 is greater than 6, so this element 7 should be on the right side, it shouldn't be on the left side of 6. So we'll stop here, and now we will go to step 5, which means we will check with j, we'll find an element by decrementing j to see if we get any element out of order there. So j, so we now start with j equal to 7, j was 8 earlier, and notice 3, and in fact 3 is less than 6. Now this is an anomaly, which means 3 has to be moved to the left side of the pivot. So we have found a place now where a j is less than p, so we need to stop and we need to swap. So we will swap 7 and 3 here, which is ai and aj, and notice I is less than j, 3 and 7, hence we will swap, which is what will be done in step 6. And once we are done, so we have 3 and 7 now, and we will again come back to step 3, which is the outer while loop. Now in the outer while loop, what we check is, we check if I is less than j. Definitely 3 is less than 7. There are more elements to be covered in the middle. So we now start with step 4 again, which means from the left side we find if there is any element that is out of order with respect to the pivot. So increment I becomes 4 now. So 4 is less than 6. So 4 is already placed in the left side of 6. So ai is less than p. So nothing needs to be done. We just increment I again. I becomes 5 now. And what we do is we check ai is less than p. No, ai is equal to p. 6 equal to 6. So our while loop will break here. So which means we have found a element which needs to be taken care of. Cool. So I will keep pointing at 5, and then we go to step 5 where we start with j and then keep decrementing j. So j is at 7 currently. So j is at 7 currently, j will be decremented to 6, and 11 is the value, and we'll compare aj with p. So aj 11 is greater than 6, so which means 11 is correctly placed with respect to 6. No need to stop here. We'll continue by decrementing j equals to 5 from 6, and once we have 6, we will see 6 equals to 6. Now in this case aj is not greater than p, which means step 5, the loop in step 5 will break, and then we will go to step 6 now, which means we have found an element that is out of order with respect to the pivot. In fact, it is equal to the pivot. Now notice what will happen in step 6. Now it will check if I is less than j, but notice I and j are pointing to the same location, so I is not less than j, so there will be no swap here. J will stop here, but there will be no swap. There will be no swap because there is no need to swap also. They are I, j and pivot are all pointing to the same location. But what happens here now is, because I is equal to j, step 6 will fail, step 6 will end, and then we will go back to step 3 again, where we will have do the check for I less than j. But notice I is not less than j, which means we have covered all the elements in the array, and now we can break the outer while loop. So once the outer while loop is broken, step 7 statement is executed, which means we just return j. So we return j equals to 5. So 5 will be returned as the value for the result of the partition. Cool. So we are done with the partition procedure. Let's go back to our original algorithm which we had and see what will happen. Now here is the original algorithm, and notice what happened here. p is returned as 5 because that is what was returned by the partition sub element, and we are now done with step 2 here. So this is how the array looks like. So 6 is highlighted because 6 is the 5th position, p is 5. So once done that, then we go to step 3. So what step 3 does is it calls the same algorithm, that is quick sort, with low and then one element less than the pivot, p minus 1. So just to indicate what happens after step 2 is the element at the pivot, which means p equals to 5, that is element 6, is now in its sorted position. But we now have two arrays, the left array and the right array. So the first, in step 3, we call the left quick sort on the left sub array, so which calls a, low, and then p minus 1, which means p minus 1 is 4, so we call a 1 4. And then in step 4 we go and call quick sort to the right part of the array, which is a, p plus 1, that is 6, and then a 6 9. So this is how the two recursive algorithms are called. So now what will happen once these recursive algorithms are called? So once these recursive algorithms are called, this will just trigger another iteration of the algorithm. So what quicksort A14 will do now is it will go through and then again call A, and then it will pass 1 here, it will pass 4 here. So low will become 1 and 4 will become, high will become 4, and then low and high are compared in step 1, which is 1 and 4, which means we still have at least 2 elements in the array. This is just to check. And then the partition P is called again. A, low, high, 1 and 4 is called. So that's what is the case. So we will call partition A4. Similarly, the right part of the array, that is quicksort A69, will just go ahead and then call partition A69 in the same way. So let's now go ahead and see what these partition procedures will do, and then we will come back and then go to step 3 and step 4, what will happen. Alright, so we now have, there was one call, now we have 2 calls to the quicksort. So we have 2 calls to the partition, one with 1 and 4 with low as 1 and high as 4, the other with low as 6 and high as 9. And the middle element, which is P, fifth element, the value of 6 is now sorted. Cool. Let's see now what happens with partition A14. So when we come to partition A14, notice how the array looks like to partition. So low is 1 and high is 4, so which means we are only concerned with the sub array 5 2 3 4 here. We are not concerned with the other part of the array. So low will point to 1 and high will point to 4, and as always we will go to step 1 now, where we will get the middle element. Now high is 4, low is 1, so this is 4 plus 1 by 2, 5 by 2. Now using integer division, this is actually 2, so which means the second element will be chosen as P. So P will point to the second element and the value is 2. P will not point, P will have the value of the second element, which is 2. So now we have P equals to 2, and in step 2 we decrement step 2 I starts from low minus 1, which is 1 minus 1 0, J is 4 plus 1, which is 5, and now we go to step 3, which means we start our while loop. So what happens in the while loop? We check if I is less than J. Definitely I is less than J, 0 is less than 5, which means we have elements to cover. And the first part is to, in step 4 what we do is we start from the leftmost, which is I. We keep incrementing I till we find an anomaly, which means till we find an element that is greater than the pivot on the left side. So I will be incremented to 1 and 5 will be compared with 2. 5 is greater than 2. So we have found an anomaly, so because 5 should be on the right side of the 2. So we'll stop I here, and then we will go ahead with the next loop on step 5, which is J, and we'll try to find an element that is out of order with respect to P on the right side. So J will now be decremented to J minus 1, so J becomes 4, and we will compare 4 with 2. 4 is greater than 2, so which is okay, 4 should be on the right side of the 2. Alright, then we will decrement J again. J is now 3, and we have found 3 is also greater than 2, so which means we still 3 is okay, so 3 is greater than the right side of the pivot. So we will decrement J again, and as we decrement J again, J will be 2 now, and notice what will happen. Because AI is no longer greater than J, AJ is no longer greater than P, so the loop, while loop here will break. Why? Because 2 is equal to 2, 2 is not greater than 2. So we have found a position for J, and then we stop here, and finally what happens is we go to step 6, wherein we swap the 2 elements that we have just found which are out of order. So it will first check I is less than J, definitely I is less than J because 1 is less than 2, and it will swap AIJ. So 5 and 2 will be swapped, so we have 2 and 5 here, and then finally step 6 is over, then we go back to step 3, wherein we start with the while loop over again. So in that case I and J will be checked, 1 is less than 2, I is 1, J is 2, so we will continue, and we will go to step 4 now. In step 4, which means again finding an element on the left side that is out of place. So I will be incremented to 2 now because I was 1, and AI will be compared with P. So AI is 5, 5 is greater than 2. So which means we have found an anomaly. So we will stop here, and then now what happens is we will go to step 5 where we have J. J was 2, J will be decremented to 1, and AJ2 will be compared with 2, and in fact this loop is also break because J is not AJ is not greater than P because 2 is 2. So this will also stop. So this case we have found an anomaly, and then we will go to step 6 here. But see what will happen in step 6. Now notice what has happened is during this process I and J have crossed each other, so we don't need to swap here. So that's what step 6 does. I is less than J, no, I is 2 and J is 1, so hence there will be no swap here. And then step 6 will end, and we will go to step 3 again, back to step 3. In step 3 we will compare I with J. What has happened is I is not less than J, I is greater than J in fact. And what will happen is the outer while loop also fails, and then finally the last statement is executed, return J. Return J means J equals to 1 here is returned, and then that value is returned to the quicksort algorithm. Alright, we will now go back to the quicksort algorithm only after some time, because we still have another partition to be sorted, the right partition, which is A69. So let's just go ahead in the similar way. We first assign low is 6 and then high is 9, and then what happens is first assign pivot P. P is 9 plus 6 15. 15 by 2 is 7.5. 7.5 in an integer arithmetic is actually 7, so which means 7th element A7 will be assigned to P. So low is 6, high is 9, and 7, which is the 7th element, is assigned to P. Alright, then I starts from low minus 1, which is 6 minus 1 5, J starts from high plus 1, 9 plus 1 10, and then we come to the while loop here in step 3 where we see I is less than J. Definitely I is less than J, we still have elements to cover, 5 is less than 10, and we will start with the first while loop in step 4, which is we will find an element that is out of order in the left part of the subarray. So I will now start with 6 because 5 plus 1 is 6, and then we'll compare 11 and 7, and notice 11 is greater than 7. In fact, it should have been to the right side of 7. So we'll stop here, and then we will now increment J, which means we'll come to step 5 here where J will now be decremented by 1. J was 10 earlier, so J now becomes 10, and we'll compare 10 with 7. Notice 10 is greater than 7, we are good here, 10 should be at the right side of the 7. So what we do is now we go ahead and decrement J further. J becomes 8 now, 9 is compared with 7, we are good, there is no need to be 9 is still at the right side of 7, which means we go ahead and decrement J again. J now becomes 7, and notice what happens, 7 is equal to 7, 7 is not greater than 7. So our while loop at step 5 will fail, and what we will do is we have found a position that needs to be swapped. So we go to step 6 now, and we'll check I is less than J. Definitely I is 6, J is 7, I is less than J, so we'll have to swap those two elements. So we stop here, we then swap 7 and 11, and finally we have 7 and 11, and what happens now is we are done with step 6, which means we will now return back to the outer loop, which is step 3, and we'll check if I is less than J. And notice I is definitely less than J because 6 is less than 7. So we'll go to step 4 now, that is the first while loop, where we advance I to the right side to find an element that is out of order. So we now increase I equals to 7, I was 6 earlier, and we'll compare 11 with 7, 11 is greater than 7, which means it is out of order. So 11 should be on the right side of 7. So we will stop here, and then what we do is we do J loop in step 5 will be decremented, J will now become 6 from 7, and 7 equals to 7, so which means AJ is no longer greater than P. So we'll have to stop here, which means now our second while loop also stops, and we go to step 6. In step 6, what we check is I and j are, if I is less than j or not, and notice what happened. I and j crossed each other, so I is no longer less than j, which means we no longer need to be swapped. In other words, we have completed organizing all the elements with respect to the element, and then with respect to the pivot, and then we do so there is no swap, and we will return back to step 3 where we'll check I is less than j. In fact, I is not less than j because I has become 7 and j has become 6. And finally we go to step 7 where we return j. Now j is 6, so we'll return j is 6. Alright, awesome. So we are done with the partition part for the second subarray as well. Let's now go ahead and look back to the original quicksort array with these return values. So this was our original array, and notice what we made the call. We first made the call to A14, the first part of the subarray, and that returned us p equals to 1. So from the first part of the subarray we get p equals to 1. Let me write it down here. And what we do is in step 2, which means the value at p equals to 1 is sorted. So 2 is now in its sorted position, and now we call quicksort on a low p minus 1. So 1 minus 1 is 0, low is 1, and then what happens is we call that is what we do, we call quicksort a10, and then we go to step 4. In step 4 what happens is we call a p plus 1. Now p was 1, this is 2, and high is 4, so we will call quicksort a24. That is what we do. Alright, cool. Now let's see what the right part of the subarray returned. So in the right part of the subarray we had made a call to quicksort a69, which had made a call to partition 69 if you remember, and that returned us p equals to 6. So which means we are the value at 6th position, which is 7, is now sorted in its place. So we will, what will happen is we will again come here, and in the second step over here we will change p equals to 6, and then we'll go to step 3 and then make a call to quicksort a65. Why? Because p minus 1 is 5 and this is 6. And similarly on the right side of the subarray we'll call quicksort a79, because p was 7, so p plus 1 is 7 and high is 9. Alright, so now we are having 4 calls. Initially we had 1 call which made 2 calls, and now from 2 we have 4 calls. Let's see what happens with these 4 calls. Now the first quicksort, which is a10, what this will do is again it will go and call the call recursively. Now what happens when the recursive call is made? When the recursive call is made, quicksort a10 will now assign low as 1 and high as 0. Now notice what will happen. Low is less than high. This condition will fail because low is now greater than high, which in other words means that there is no element on the left side. There is no element in this array to be sorted. So we just return. We don't do anything. And then that's what we do. We return here. So a10 no longer does anything. It just returns back. Awesome. Now what happens with the next quicksort? Now the next quicksort calls a24, which is 2 and 4, so low is 2 and high is 4, and notice low is less than high, which means we just move ahead. And then in step 2 we'll go ahead and call a partition 24. So what this does is it goes and calls a24. Awesome. We will go to the partition procedure after some time, but now let's see what the other 2 quicksort calls also do. So the next quicksort call which we have is a65. So what that will do is it will assign low as 6 and high as 5, and notice what will happen. This if condition will fail because 6 is not less than 5. In other words, there are no elements in this array to be sorted, so we will just return. So we don't need to do anything, and this call will just return. Awesome. And then finally we have quicksort a79. So this will call partition a79. Why? Because we have low as 7 and high as 9, and this will go to step 2 and call 7 and 9. So in summary, we now have two calls to be made, two partition procedures that need to be executed, which we will now do next in the next step. So let's now go ahead and do these partitions one by one, these two partition calls, and see what they return. Alright, so the first call is partition A24, which means low is 2 and high is 4, which means we just have 3 elements to be sorted in this case. As always, we start with P equals to high plus low by 2. So high plus low is 2 plus 4, which is 6. 6 by 2 is 3. So this is A3, so P will be 3, and the element at third position is 3 luckily, so P becomes 3 here. Awesome. Then in step 2 we start with I equal to low minus 1, so I is 2 minus 1, which is 1, and j equals to 4 plus 1, that is 5. Cool. Now we go ahead in step 3 where we check I is less than j. Definitely I is less than j, which means there are elements to be sorted or processed. We'll go to step 4, which is the inner while loop, where we increment I till we find an element that is out of order. So in this case we increment I becomes 2, and then we compare the value 3, which is value 5, which is greater than 3. So we have already found an element that is out of order, so the element that should be on the right side of P. So what we'll do is we will stop here, and then now we will go to step 5, which is in the j loop, where we decrement j till we find an element that is out of order there. So j now gets decremented to 4 from 5, and then we'll compare 4 with 3. So 4 is greater than 3, which means 4 is perfectly placed with respect to 3. There is no need to do anything, so we'll decrement j again. J now becomes 3. Now the value 3 is actually equal to 3. 3 is not greater than 3, so our j loop will stop here because aj is no longer greater than p. So what we will do is we will go to step 6 now. In step 6 we check I is less than j, which is because I is 2, j is 3, and then we'll swap the two elements because 5 and 3 can be swapped. So we stop here, and then we'll swap 5 and 3, and finally we have 3 and 5 and then 4, and I was pointing so we swap these two elements in step 6. Then we will return to step 3. Now in step 3 what happens is we check I is less than j. I is definitely less than j because I is pointing to I is pointing to 2 and j is pointing to 3, I believe, right? J is, let's just check, I is pointing to 2 and j is pointing to 3, so I is less than 3. So what will happen is the inner while loop will trigger again. So in this case what happens is I will be incremented so I will be incremented to 2 plus 1, 3, and 5 will be compared with 3. 5 is greater than 3, which means we have again found an anomaly. So our outer while loop, the while loop will break now, and now we go to the next while loop in step 5, which is decrement j till we find aj is find the element aj is greater than p. So we have j equals to 2 and the value 3 is actually equal to 3, which means we don't need to decrement j again, and the while loop will stop. So what happens now is we go to step 6. Now in step 6 what happens is there is a check if I is less than j, which means just a check if I and j have crossed each other, and in fact they have. That's why the swap will not happen. So which means there will be no swap, and we will go back to step 3 again, the outer while loop. In outer while loop we again check for while I is less than j. I is not less than j, I and j have crossed because I is 3, j is 2, so which means we now exit the outer while loop, and once we exit the outer while loop we'll run the last statement, which is return j. So we just return j equals to 2 as a result of a call to this partition procedure. So j is returned as 2. Awesome. Now let's go ahead and run quick sort or run partition on the right partition call that was there. The right partition was A79, and similarly we start with low as 7, high is 9. So pivot P is high plus low by 2, so 7 plus 9 is 16 by 2 is 8, so 8 is basically the 8th element, the value is 9, so we'll assign p equals to 9 here. Once we do that, we first start with I equals to low minus 1, so I will point to 7 minus 1 6, j will point to high plus 1, 9 plus 1 10, and then we start the loop in step 3. I is less than j, definitely, because 6 is less than 10, so we start with first finding an element on the left side, that is using I in such a way that the element is larger than the pivot. So we'll keep incrementing I will become 7 from 6, and 11 will now be compared with 9. Definitely 11 is greater than 9. The element is out of order, which means we'll stop here. So this is a perfect candidate for swap. Then this while loop will break, and we'll go to the next while loop where we will decrement j till we find an element on the right side that is out of order. So j starts with 9, it was 10 earlier, and 10 will be compared with 9. 10 is greater than 9, so this element is correctly positioned, no need to do anything, and just decrement j again. So j will get decremented to 8, j gets decremented to 8, and we will see that 9 is equal to 9. Because aj is not greater than p, so we will stop here. So this while loop will stop, and then we will go to step 6. In step 6, what happens is I is compared with j, so I is definitely less than j, which means these two are perfect candidates for swap. I is 7, j is 8, and then 9 and 7 are swapped. 9 and 7 are swapped, but we will now have 9, 7 and 10, and we will go back to step 3. In step 3, we compare I and j, and I is definitely less than j, due to which we will go to step 4, which means we'll keep incrementing I till we find an element that is out of order on the left side. So I is incremented from 7 to 8, and AI 11 we will compare with 9. 11 is greater than 9, so we'll stop here. This loop will stop here. We'll go to step 5 now. In step 5, j is decremented. J was 8 earlier, so j will get decremented to 7, and we will see that 9 is equal to 9. So 9 is not greater than 9, which means we have to stop here. We'll stop here, and then we go to step 6. In step 6, what happens is I is compared with j, and notice what happened, I and j crossed each other, which means we don't need to swap, so no swap will be done here. And what will happen is we will go back to step 3 here again. In step 3, I will be compared with j. Now notice I and j have crossed, so I is no longer less than j, so which means we break here, outer while loop, and finally the return j statement is executed, which means we return j equals to 7. Alright, we have finished the two partition calls now. Now let's go back to the original quick sort algorithm and see what we do with these returned values from partition. So this was our original array, and we had about 3 elements already sorted. Now the first call to quicksort A to 4 resulted in calling partition A to 4, which returned back value as 2, j equals to 2 or p equals to 2. So which means we now have element 3 in its position. And now we go to step 3 and 4, and we will call low and 1 because p is 2, so it's 1 a low is now 1, and p minus 1 is low is not 1 here. In this case, low had become 2 because low is 2, high is 4. So we have 2, p minus 1 is 1, and then it will call quicksort A to 1. Similarly, the next in step 4, what it will do is it will call p plus 1 high. So p is 2, which means 3, and then 4. So this will call quicksort A 3 4. Awesome. Now let's see what the right side of the partition resulted in. So the right side made a call to A79. Now A79 is basically called partition 79. So partition 79, so 79, and this returned back p equals to 7 as a result. So what will happen is we will now go to step 3 and make a call as 7, and then p minus 1 is 6, p plus 1 is 8, and high is 9. So we'll make two calls, quicksort A76 and quicksort A89. Alright, so 4 more calls. So 2 calls were completed, but we made 2 calls to partition, which resulted in 4 calls to quicksort. Now let's see what each of these will do. So quicksort A21, as we can see, because low is less than high, low is not less than high in this case. So in this case what will happen is 2, low will be 2 and high will be 1. So low is not less than, low is less than, not less than high, so which means there are no elements to sort in this array. So it will just return back, it will not do anything. Awesome. Now let's go to the next call, which is quicksort A34. So what quicksort A34 will do is it will call 3, which means low is 3 and high is 4, and this will in turn call partition 34. So partition 34 will be called. Now the next one, which is quicksort A76, this is similar to the quicksort A21, wherein the low becomes actually greater than the high. So if we put value here 7 and 6, 7 is not less than 6, so this will just return, not do anything. There are no elements to sort here. And finally quicksort A89 will call A89 or partition A89. So what it will do is it will have low as 8 and high as 9, so this will call partition 8 and 9. So in short, 2 calls will be useless, and the other 2, which we will see now, A34 and A89. So these are the 2 partition calls. Awesome. So let's go ahead and do the first one, that is A34. Now notice our elements have only reduced to 2 now. So high is low, low is 3, high is 4, and p will be a high plus low by 2. So 3 plus 4 is 7. 7 by 2 in integer arithmetic is 3. So which means third element will be p. So low. So p will now be a3, which is 5. Awesome. I will be low minus 1, which is 2. J will be high plus 1, which is 4 plus 1, 5. And then we will go ahead and then go to the loop in step 3, which says I is less than j. Definitely I is less than j, which means we still have elements to process. 2 is less than 5. And then we'll first start with finding an element on the left side, which means we'll keep incrementing ai till we find an ai that is greater than p. So I is incremented to 3, 5 is actually equal to 5. So which means we have to stop here. Sorry, because the inner while loop on step 4 will fail, and we have a perfect candidate for swap. Awesome. Then we go to step 5. In step 5, what happens is we again have we will now decrement j till we find an element that is out of order with respect to p. J was 5, j now becomes 4, aj is 4, so 4 is less than 5. And notice this should be on the left side of 5. So this means actually this needs a swap. So we have to stop here, and once we stop here, we have found perfect aij for swapping. So we go to step 6, where we check I is less than j. Definitely I is less than j, I is 3, j is 4, and then we swap ai and h. So 4 and 5 get swapped, and once 4 and 5 get swapped, we now go to step 3 again, where we check if I is less than j. And notice I is still less than j because I is 3, j is 4. Now we will go inside and start with the I loop, which means increment I till we find an element that is out of order. So this will not do much. What it will do is I becomes 4 now, and 5 is now equals to 5, so which means this while loop will stop. 5 is not less than 5, and we'll go to step 5, where it's the j loop. So in j loop we'll decrement j will be decremented to 3 from 4, and what will happen is 4 will now be compared with 5, and 4 is actually less than 5, so which means we will have to stop here. Excuse me. And we will go to step 6. But what happens in step 6 is, since I and j pointers have crossed each other, so I is no longer less than j, and hence there will be no swapping here. And what will happen is step 6 will end, and we'll go to step 3, where I is again less than j is compared, and I is not less than j, so the outer while loop will also end, and we will go to step 7 and finally return j equals to 3, which is the value of j. Awesome. So A34 returns j equals to 3. Now let's go ahead and do the other part of the partition call which was left, which is partition A89. Now similarly proceeding, we'll have low as 8, high as 9, and p equals to 8 plus 9, 17 by 2. In an integer arithmetic, 17 by 2 is 8, so p will point to the 8th element, which is 11. Awesome. And I will start with 8 minus 1 7, j will be 9 plus 1 10, and what we will have is we go to the we go to the while loop, which is I less than j is compared, definitely, because 7 is less than 10, and we'll first start with the left side and increment I till we have found an element that is greater than the pivot. So I now becomes 8, and 11 is now compared with 11, and 11 is actually equal to 11. 11 is not less than 11, so this while loop will end here. We'll stop here, and now then we will go to the next while loop, which is j equals to 1, sorry, which is the j loop, where j will be decremented. So j was 10, j now gets decremented to 9, and we have a j which is 10 less than 11. Cool. So this element is out of order. 10 should be to the left of the 11. So I found a perfect position for swap now. So this loop will stop, and we go to step 6. In step 6, I and j are compared. I is less than j because I is 8, j is 9, and we do swap aij. So 10 and 11 are swapped, and 10 and 11 are now swapped. And once that is done, we will go to step 3 to see if I and to check the outer while loop. I is still less than j because 8 is less than 9. So we'll go to step 4 then. In step 4, we will increment I and then see if ai is less than p. So we increment I is 9, and 11 equals to 11. So in this case, now there is a mistake here, this should be 11. So 11 is equal to 11, so the outer while loop will break. Similarly, the step 5 will decrement j. J now becomes 8, and aij will be compared. 10 is less than 9, so which means this while loop will also break here. This while loop will also break here, and we go to step 6. In step 6, notice what happens. I is no longer less than j, so the swap will not happen, and we'll return back to step 3. Now in step 3, what happens is we compare I with j. I is no longer less than j, which means the pointers have crossed each other. So we will break the outer while loop, and finally we will return j, which is nothing but j equals to 8. Cool. So these two calls to partition return back two values. Now let's see what those values are. So this is what we have, and the first call to quicksort A34 resulted in partition 34, and that returned back p equals to 3. So the value j equal to 3 was returned here. And then what happens in this case, we call quicksort a low p minus 1. Low is 3 and p minus 1 is 2. And the next call to quicksort p plus 1, which is 4, and then high is 4. Awesome. So let's see what happens here. So we'll have A32 and A44. Now similarly, on the right side, what we will have is the right side of quicksort A89 called partition A89, which has returned p equals to 8. So let me write 8 here, and this will result in two calls. The first one is A87, 8 and then 7, and the next one is 9, and then high is 9. Awesome. And notice what happened, the element at the position p was sorted. So 4 and 10 were in sorted position. So as such, we now have 3, 2, 3, 4, 6, 7, 8, 9, about 7 elements in its sorted position after so many calls to quicksort. Awesome. Now let's see one by one what A3 each of these calls to. So the first call is A32. So A32 will result in calling low as 3 and high is 2. So 3 and 2, and notice what will happen, because 3 is no longer less than 2, this call will return. So this call will do nothing and it will just return. Awesome. The next call is A44, which will return, which will compare low and high. So low will be 4 and high will be 4. So low is 4 and high will be 4. Again, notice low is not less than high. So this will also return. So there is no more calls. In other words, because we only had one element by itself is sorted. There is no need to reposition. So in the first call there were no elements, in the second call there was one element, and the same thing happens in the next two calls, that is A87. Now A87, because low is less than high, will just return. There will be no elements to be processed in this case. And lastly A99 will have low as 9 and high as 9, and this means it only has one element. There is absolutely nothing to do here. So which means we are done. And if you see, really we are actually done, because single elements no longer need to be sorted, and our final sorted array is just this 2, 3, 4, 5, 6, 7, 9, 10, 11. Awesome. So after these long steps, we have finally completed the sorted array. I hope this description, although it was very lengthy, little longer, but it helped clarify how the algorithm runs. And finally we are done with sorting the array using quicksort. Alright, so let's now go ahead and see the next part, which is to see the time complexity or the performance of quicksort. Now quicksort is not a simple algorithm to do its complexity. It has in fact two parts. The first is the partition. So let's first see the partition algorithm and how it runs. So in partition algorithm there are three while loops, and in fact there are two while loops inside of the first while loop. But if you notice, those while loops, they actually all run on the same value. So the inner while loop runs on I, outer while loop runs on j, and the inner while loop actually is just moving right, and and the inner j loop is just going left, until this occurs, till both of them collide with each other, and I starts from low. If you remember, I starts from low and j starts from high, and the outer while loop also just helps the inner loop. So these are not different variables, so it's just I and j are starting from the left side, and I is starting from the left side and j is starting from the right side, and then they just move one by one to cover each elements. And notice none of the element is actually repeatedly covered, because if an element is covered by I, it's no longer covered by j. So what happens in this case is total comparisons that we are making is nothing but just high minus low. So the high one and the low, if we just subtract, it's just high minus low or high minus low plus 1. In other words, it's just n comparison. If we say, the size of A that was given is n, then it's just n comparisons with P. So at max we make n comparisons with P, which is nothing but order n. So which means the partition algorithm runs in order n. Definitely if the size has reduced to n by 2, it will be n by 2, but given that the size of the array A is n, we say that total comparisons or the time complexity of partition is actually order n. Awesome. Let's see now the original quicksort call. So quicksort call is nothing but a recursive call. So first we have the partition call, which has high minus low, that is order n. Then we have two calls. The first one is a p minus 1, low to p minus 1, and second is a p plus 1 to high. So in this case, what is the time complexity? Now this is a recursive algorithm. So for recursive algorithm, we can write a recurrence relationship and then compute the time complexity. So let's say if Tn was the time complexity of the original algorithm, then the total time complexity is order n, this is for the partition, plus Tp minus 1 plus Tn minus p. Why? Because what we have done is we have decrease the size or decrease the complexity of the original quicksort, which was n, to have now p minus 1 elements. Let's say in this case first we start with low equal to 0. The first one will have p minus 1 elements, so which means it is nothing but Tp minus 1. So the time complexity of quicksort with p minus 1 elements, and then the next one is high minus p minus 1, which is nothing but n minus p elements. So this is the time complexity, and it will depend on, as you can see, the time complexity of this algorithm will highly depend on what p is. And that's why there is a lot of research on finding what is the best pivot or how to find the best optimized pivot. And we will now see what happens in the various cases for time complexity. Let's go ahead and do that. So what happens in best case? Now the best case is actually for quicksort when array gets partitioned exactly into 2 parts every time. So which means if there are 8 elements, we are recursively partitioning it to 4 and 4, and then 2, 2 and 2, and then 1 and 1, because this ensures that we end up in lower number of quicksort calls. And this is when the best case of quicksort occurs. Now when this occurs when p actually partitions the elements into 2 parts, which means the left part is n by 2 and the right part is n by 2. So this occurs when p equals to n by 2 or p equals to n by 2 plus 1, but approximately n by 2. So due to which what happens is the complexity of Tn reduces to order n plus Tn by 2 plus Tn by 2. So it's 2 Tn by 2, order n plus 2 Tn by 2. So if we solve this recurrence relation using Master's theorem or just by repeated insertions, we will have Tn equals to order n log n. So this is the final complexity in case of best case. So best case quicksort runs in order n log n. So if you want to go back and verify the original video we had on sorting algorithms, you would see that. And similar cases with average case. So in average case and best case quicksort perform similar. So we are assuming that the division is somehow fair, division of the array is somehow fair, not worse, which means it's not into 1 and n minus 1, but it's somehow proportional to n, like n by 4 and 3n by 4. So in this case also, if we compare, and we will get order of n log n. So in average case and best case both, it's order n log n. Now let's go to the worst case, which is a little different. Now when does the worst case occurs? The worst case occurs when actually array is very badly partitioned. So this is when array is actually partitioned into 1 and n minus 1. This is very bad partitioning, which means in every call of the hierarchy we are only reducing the element by 1. So in this case looks very similar to the passes that we had in the basic sorting algorithms, which is insertion sort and all that, insertion sort, bubble sort, and selection sort. But what happens in this case? Let's just put the values in our recurrence relation. So we have Tn is order n, and we have two sub arrays now. One is n minus 1 and one is 1. So T1, let's say, is probably just a number. This is a constant. So if we solve this recurrence relation, we will have Tn is equal to order n square. So this is what happens. So in worst case, this actually performs order n square, which is similar to selection sort, insertion sort, and bubble sort. Awesome. So I hope this complexity analysis was clearer. If not, make sure to write a comment on the video, and I'll definitely respond you back with more details. And finally, before we end, here is an exercise for you. So use quicksort to sort this given array. List the total number of comparisons needed and see what is the total count of the comparisons needed. Compare it with n. So in this case n is 10 because we have 10 elements, and see how many comparisons you totally need to sort this array. Awesome. So that concludes this video, and I hope you guys liked the video, and I hope the explanation was pretty detailed and clearer. If not, please do comment on this video and I will see where things can be improved. If you want any other videos to be covered related to sorting or anything on computer science, you can request me and I'll try if I can cover them. Alright, so bye bye. Thanks for watching the video. See you again next time.